Okay, Assalamualaikum and good day to everyone. So in this video, we will learn chapter 3, okay, Kinetics of Particle, subtopic number 2, which is work and energy. Okay, so introduction. Kinetics or motion of particle can be analyzed by using method of force and acceleration. Okay, F equal to ma, and it can be derived to obtain another equation, which are work and energy principle, okay, and also impulse and momentum principle. Okay, so from work and energy principle, we can find F, V, and S, and from impulse and momentum principle, we can find force, V, and T. Okay, so learning outcome upon completion of this chapter, student will be able to calculate the work of force and apply the principle of work and energy to a particle or system of particle. A force does work on a particle when the particle undergoes a displacement along the line of action of the force. Okay. So work is defined as the product of force and displacement components acting in the same direction. Okay, so work is equal to F cos theta T. Okay, from this picture. Okay, energy is required to do work, and the basic SI unit of energy is joule. The amount of energy required to exert a force of 1 Newton through a distance of 1 meter. So 1 joule equal to 1 Newton meter. Okay, so we have special case which is no work done. First, when force without motion. Okay, so when a force is exerted on an object which does not move, no work done is on the object. Okay, and the other special case is when the force is perpendicular to the motion with constant velocity. Okay, so when an object is carried at constant velocity by a force which acts at right angles to the motion, no work is done on the object. Okay, next, if the angle between the force and displacement vector is theta, okay, the increment of work done by the force is equal to du F ds cos theta. Okay, or by using the definition of the dot product and integrating, the total work done can be written as, okay, work done from 1 to 2 equal to limit from R1 to R2 F dr, or scalar work done from 1 to 2 equal to S1 to S2 F cos theta ds. Okay, next, if both F and theta are constant, okay, this equation further simplified to U from 1 to 2 equal to Fc cos theta S2 minus S1. Okay, so S2 is the S final, S1 is the S initial. Okay, and the important tips is work is positive if the force and the movement are in the same direction. Okay, and if they are opposing, the work is negative. Okay, if the force and the displacement direction are perpendicular, the work is 0. Okay, so there are the important tips. Okay, so we move to the types of work. Okay, so the first type is work of applied force or we write as UF, and work of weight force UY or UW, and the work of spring force we write as US. Okay, so first, work of applied force UF. Okay, if both F and theta are constant, this equation further simplify to UF equal to FC cos theta times S2 minus S1. Okay, so U1 to 2 is the total work done, F is the applied force, S1 is the initial displacement, S2 is the final displacement, and theta is the angle between force applied and the displacement. Okay, so as you can see from the picture, S1, S2, force, angle, and distance. Okay, and again, work is positive if the force and the movement are in the same direction. If they are opposing, then the work is negative. If the force and the displacement direction are perpendicular, the work is 0. Okay, next, work of weight force. Okay. Displacement from the figure, displacement Y must be measured from datum. Okay, so we set our datum here, Y1 and Y2. Okay, so from general equation of work, F ds cos theta as displacement in Y direction, so U from 1 to 2 is F dy cos theta. Okay, force and displacement are in opposite direction and no angle between them, so cos 0 is equal to 1. Thus, uy equal to negative w y2 minus y1. Okay. Next, work of spring force. Okay. Magnitude of the force exerted by a spring is proportional to deflection. So F equal to Ks. Okay, where K is spring constant, X is stretch length equal to displacement S. Okay, so from the equation we have two, S initial and S final, or S1 and S2. So the equation of the spring will become US equal to negative half KS2 square minus half KS1 square. Okay, so to find S, we use this formula. So length total 1 equals to L naught plus S1 and LT2 equal to L naught plus S2. So what is L naught? Okay, L naught is the initial length or unstretched length or original length. LT1 is total length at position 1. LT2 is total length at position 2. And X or S is stretch length or elongation line. Okay. So at initial, we have initial length, okay, LO. Okay. Next, position 1, we have LT1 and X1. Okay. And for LT2, we have LT2 and X2. Okay. So let's do an example. Okay. Find work of a spring when the slider move from 1 to 2, okay, from 1 to 2, it has an unstretched length of 4 meter. So L naught equal to 4 meter. Okay, we know that work for spring is equal to negative half ks 2 square minus half ks 1 square. Okay, next step, you need to find what is S1 and S2. Okay, so from the formula, length total 1 equal to L naught plus S1. You know that L naught is 4 and LT1 is equal to this length. Okay, so how to find this length? Okay, you have 3 here and 4, so automatic LT1 is 5. Okay, substitute to the equation and you will get S1. Okay, next find S2. Okay, we know that LT2 equal to L naught plus S2. Okay, so LT2 when the spring at 2. Okay, so when the spring is at 2, LT2 is 3 meter. Okay, substitute and you get the answer for S2. Okay, after that, just substitute to the equation. Okay, and you will get 0 joule. Okay. Okay. Principle of work and energy. So this slide tell us about how to derive the equation. Okay. So work done is equal to change in kinetic energy. Okay. So the principle of work energy equation is half mv1 square plus summation of work from 1 to 2 equal to half mv2 square. Okay. So half mv1 square, also known as T1, which is initial kinetic energy. Summation of work from 1 to 2 is the total work done. Okay. The summation of work done by force plus work done by weight and work done by spring equal to T2, which is final kinetic energy. Right? Okay. Next. Sorry. Okay, next. Let's try the example 1. The spring has a stiffness K equal to 200 Newton per meter and an unstretched length of 0.5 meter. If it is attached to the 3 kg smooth collar and the collar is released from rest at A, determine the speed of the collar when it reaches B. Neglect the size of the collar. Okay, so for the solution, write down the information from the question. Okay, we know that K is equal to 200 Newton per meter. Unstretched length LO equal to 0.5. M is 3 kg. Collar is released from rest. So V1 is equal to 0. Okay, and from the principle of work and energy, we have half mv1 plus summation of work done from 1 to 2 equal to half mv2 square. Okay, first step is to find T1 and T2. Okay, so as we know that the colloid is released from rest, so T1 will become 0. Okay, and T2 we have half 3 V2 square G. Okay, next, second step, find total work done. Okay, so work done from 1 to 2, UF plus UY plus US, and there is no force, so UF is equal to 0. So we find work of weight force, UY, so UY equal to negative W Y2 minus Y1. Okay, so mg, okay, Y2 is negative 2 minus 0. Okay, we get 58.86. Next, work of spring force, US equal to negative half KS2 square minus half KS1 square. Okay, find S1 and S2 first. Okay, so S1, LT1 equal to LO plus S1. Okay, so the LT1 is here. Okay, so find LT1. So LT1 is equal to square root of 2 square plus 1.5 square. So we get 2.5, and then substitute, we get S1. Okay, same goes to LT2. Okay, LT2, when it reaches at B, so LT2 is equal to 1.5. Okay, substitute and get the 300 joule. Okay, please try by yourself and understand how to find the answers. Okay, next, okay, we need to find V2. Okay, so substitute to the equation, mv1 square plus summation of work done from 1 to 2 equal to half mv2 square. Okay, substitute and get the answer for V2. Okay, so please try example 2. Okay, try example 2 by your own. Okay, if there is any question, you can ask me. Okay, so that's all for this video. Thank you so much, and Assalamualaikum.